Hi, my name is Hans Lindetorp and I wish to present WebAudioXML for you today. We are proposing a new standard for structuring web audio, and the study is done by me and Kjetil Falkenberg, and we are from Royal College of Music in Stockholm and Royal Institute of Technology in Stockholm, Sweden. So, what is WebAudioXML? It is an XML language for structuring audio graphs. It lets you connect audio parameters in an audio application to external events and variables. It's built upon something called WebAudioAPI, which just 2 years ago became a web recommendation, and that is great because that means that WebAudioAPI is available on almost all devices with a web browser. That makes it possible to build audio applications that could be online, and you can share it with just a link. And there are lots of projects running already, professional, pedagogical, and more like researchal applications. At the Royal College of Music, we have an education in music production, and those students are great. They love audio, they love music, they love technology. So they could potentially be great contributors of applications using WebAudioAPI, but they don't know how to program. So just to learn as much JavaScript that would be needed to be able to do something interesting, that would take a long time for them. But they know some HTML because we have like basic classes in web design connected to music. So that was why we came up with the idea to do something with XML, which is fairly similar to HTML. So that is WebAudioXML. And before we dive deeper into the technology, I want to show you 3 examples of what you can do with WebAudioXML. And the first example is a synthesizer. It's online. And it's actually running right now online from CodePen, a CodePen project. So you can see to the left here the graphical interface, and to the right the XML code. And I am playing the synth from my external MIDI keyboard, so it's using WebMIDI API as well. So it works like that, and it works like expected. You have the attack, sustain, decay, and release. And we can change, this is an FM synth, so we have a modulator and a carrier oscillator, and we can change the pitch of the modulator, which changes the sound quite dramatically. Okay, so that was playing on the synth. This is how the synth is built using WebAudioXML. So you can see 2 chains here. One for the modulator, which is outputted to the carrier down here. And both oscillators are controlled. The gain of the oscillators are controlled with an envelope as well. And those values, attack, decay, sustain, release, are connected via the follow attribute to the graphical interface. So that's how it's working. Next example, that is a very simple game, but it gives you an idea of how you can use WebAudioXML to do game audio. So we have a spaceship and an enemy. As you can hear, the sound changes depending on how close I get to the enemy. We have sound effects as well. Oops. And the higher the score gets, the more music I get. And this application was built like this. So we have the music up here, 2 loops running through a gain node controlled by the score, and a bytecode filter set to low pass, also controlled with a score, mapping the value of the score to frequency values for the filter. We have the spaceship with the bandpass filter and the Q value that will follow the distance to the character from the enemy. And then we have a whole bunch of sound effects as well. So that's how that's built. The last example is very new. We just got it. It's one of the student projects. It's done for smartphones. So it's kind of a game. You're supposed to press this button. And hearing the sound. And then you're expected to imitate the sound. Well, maybe not exactly. So, but as you could see, the sound changes on the x-axis and the y-axis. So it's the formants that are changing. And this is how it's built. So we got the oscillator running through 2 bytecode filters. And the Q value and the frequency values are following the relative X value and the relative Y value and mapped to sensible values. So, what does WebAudioXML offer? Well, it offers a hierarchical structure that gives a picture of the audio graph when you code it. It's a relatively easy entry into audio development for beginners, and it also offers rapid prototyping. And it helps creators to focus more on the artistic ambitions and visions rather than all the technical aspects and issues that you might get stuck in. What is done so far? Well, we've set up a GitHub page with open source code and documentation so people can learn, dive into it, and maybe contribute as well. We have a CodePen collection with lots of laboratory examples where, for example, students can go there and try out the examples and learn by changing the code themselves. We also set up a YouTube playlist with tutorials to make it easy to get started. How did we do this process? So it started off with years of experience with student projects using Web Audio API at the Royal College of Music. And that brought us, as I told you, to the point where we thought we should try something else. And we tried the XML approach. And we built a prototype and evaluated it with a group of sound and music computing experts in Stockholm. And the feedback we got from that session took us to the beta phase that was evaluated with professional composers and music producers at the Royal College of Music. And the feedback we got from that session took us to version 1.0 that was released and tested during the spring with more than 25 student projects. And we just got the results back, so that's great. And what did we learn? Well, the feedback we got both from students and experts was that this technology is great for learning. It's great for prototyping and for sharing ideas and productions, small productions. And also good for collaboration when you could use, for example, CodePen to write code together. But they also expressed some needs and wishes. For example, professional debugging and testing tools to be able to use the technology more smoothly. And they also asked for modular structure with the files, with shareable components that could be put in repositories and shared with the community. So that's actually built into the current version of WebAudioXML. We also got a request for a JavaScript API. So when you build the structure with XML, you might actually want to go further and to do exactly what you want with that parameter in the graph. So they asked for a JavaScript API to do that. specific task with the audio parameters. So what is next? Well, we are currently doing a follow-up study on those student projects to see what they did, to see what they learned, and so that will be exciting. And we're planning to present it in December this year at the Web Audio Conference, where we also want to discuss the potential for a future standard like WebAudioXML. It would also be great to open up the technology for JavaScript plugins like web audio modules and web audio plugins, maybe even WebPG. So that would be really great. And with those words, I want to say thank you very much for listening, and please visit the GitHub page, and don't hesitate to contact us if you want to collaborate or if you have further questions. So thank you very much.
Okay, we are ready to start now. Thank you for taking the time out of your busy schedule. I'm Kato, the student of the University of Tokyo. Today I'm talking about Web 360 Square, an interactive web application for viewing 3D audiovisual contents. This is today's outline. First, I will talk about the introduction, our research background, and then I will introduce 3 methods of 3D sound representation and 3 interactive 3D audiovisual services. Next, I will talk about my study, Web 360 Square, and summary of questionnaire responses, and finally talk about future work. Okay, let's start. In recent years, the use of video streaming services has expanded rapidly. According to the 2018 Global Internet Phenomena Report released by Sandvine, video streaming accounts for about 58% of all downstream internet traffic. With the continuing adoption of VR services, 360-degree video streaming has also attracted. YouTube, Facebook, and Netflix offer support for 360-degree video and 3D sound. Those video streaming services have applications for web browsers in addition to dedicated applications. The web is an environment that anyone can easily use, and now supports the playing of 360-degree video and 3D sound, for example 3JS, A-Frame, or WebAudio API. But there are a few web applications that can play 3D content interactively. In our study, we designed and implemented a web application called Web 360 Square, which plays 360-degree video and object-based 3D sounds. Various methods exist for representing 3D sound. MPEG 3D audio, which is a 3D audio standard, supports 3 methods: channel-based, object-based, and higher-order ambisonics HOA-based audio. First, channel-based audio is known as traditional 2.0 channel stereo sound, and there are 5.1 channel surround sound or immersive sound with additional channels. It provides optimal sound performance for a predetermined number of speakers and speaker layout. However, it lacks flexibility and interactivity. Object-based audio uses sound objects which have spatial coordinates, and it renders optimal 3D sound for speakers in real time using those coordinates. In addition, each sound object is managed independently, so object-based can use flexible and interactively. Higher order ambisonics HOA-based audio records a spherical sound scene spread around one point. The spherical sound scene can be easily rotated in synchronization with the listener's head rotation. HOA is also flexible for speaker layouts, but HOA doesn't have clear spatial information, so it's difficult to access each sound object in the sound field. I will introduce 3 interactive 3D audiovisual services. Inside Music is an experimental website published in 2017 by Google Creative Lab and Song Exploder that uses JavaScript frameworks of WebVR and WebAudio. You can enjoy 3D sound with object-based audio in a virtual space on the web. It is not necessary to install a dedicated application. Only a web browser is needed. In Inside Music, only object-based sounds, not 360-degree videos, are mapped in a virtual space. In our previous research, we designed and implemented STM360 Square and Vibration, which are interactive 3D audiovisual services for tablet devices or VR head-mounted displays. Both systems were developed using the Unity platform, not web. Here talk about Web 360 Square. We designed and implemented the interactive web application for 3D audiovisual. In the table, we summarize a comparison between the related systems and Web 360 Square. The most important point is the environment is the web. Then the comparison target is Inside Music, but as discussed earlier, Inside Music doesn't use 360-degree videos. Our Web 360 Square is published on GitHub pages. The URL is on the slide. This system is built with A-Frame and WebAudio API. Let's give you a short demonstration. When you move the tablet device, the view angle is changed by a gyro sensor. Tapping the front cyan sphere toggles play and pause. You can turn each sound on and off by tapping these audio visualizers. When you turn to the right, you'll hear the sound from the left. If you wear a headphone, it's especially easy to hear. Another content is a concert. This figure shows the overview of system design. The process is in A-Frame mainly to project 360-degree video on a virtual space and to map audio visualizer onto it. A-Frame also changes the viewing angle. WebAudio API renders 3D sounds in real time and gets frequency data of each sound source. The left figure shows the system implementation. This dashed border field represents the A-Frame process, and this field represents the WebAudio API. The middle field here is for connecting the two fields. The right figure describes the process of an audio visualization. Frequency data is obtained by the WebAudio API on each tick, the order of 60 to 120 times per second. We extract the upper and lower limits of the frequency in which a valid value has appeared at least once, and define this band as the valid frequency band. Then the valid frequency band is divided into 32 groups. The average value is calculated within each group. The audio visualizer has 32 needles that have one-to-one random correspondence to the 32 valid frequency groups. We conducted a subjective evaluation of the Web 360 Square through a questionnaire survey that was carried out at Lindetorp Tokyo 2019 between June 12 and June 14. We prepared 2 sets of iPad tablets and headphones and accessed Web 360 Square on Safari browser. The subjects were 93 visitors to Interrupt Tokyo. First, we provided an overview of the application and explained how to use it. We then let the visitors freely play with the application and evaluate it. After the experience, the visitors completed their questionnaires and we acquired the evaluation data. The questionnaire contained 6 questions as shown on the slide. It was evaluated using the 7-point Likert scale, ranging from 1 to 7. 1 is very poor, 4 is fair, and 7 is excellent. This figure shows the result. The middle of the response of 4 is aligned with the origin of the horizontal axis, while responses of 5, 6, and 7, indicating good evaluations, are arranged in the right direction, while responses of 3, 2, and 1, indicating poor evaluations, are arranged in the left direction. As you can see, it is highly rated overall. However, there were not a few poor evaluations for question 3. Question 3 inquired about the 3D effect of the synthesized sound. We believe that this was caused in part by the ambiguity of question 3. It is thought that multiple elements including direction, depth, and spatial realism form the 3D effect of sound. It was difficult to the subject to clearly understand which element the question was referring to, and we didn't know which element the subjects were referring to. Therefore, we will more carefully verify the precision of our questions in future surveys. In the future, we will promote integration with SD ontology. What is SD ontology? SD ontology can describe the multimedia recording metadata in a layered structure. The metadata is, for example, the location information, the orientation of the musical instruments, the venue information, the recording process, and so on. We will promote integration and fetch the metadata used in Web 360 Square from SD ontology. And we also improve and add features and fix bugs on Web 360 Square. In addition, we would like to carry out the network performance evaluation. This is all for my presentation. Thanks for listening.
Hello all, I am Federico Simonetta, and together with Federico Avanzini and Stavros Ntalampiras from the University of Milan, the Music Informatics Laboratory, we have written this paper about an automatic framework for compiling multimodal datasets with audio and scores. The main motivations are explainable with 3 keywords. The first one is multimodality. So the idea that we can exploit multimodal data, so different kind of data such as video, music recording, lyrics, images, and so on, for common MIR tasks. We think that the web already allows end user to exploit multimodal approaches, but the problem is that we need datasets to train and to develop multimodal computational techniques. A second motivation is to improve the reproducibility of the research. Reproducibility is one of the main concerns of contemporary scientific research, and in music information retrieval it usually occurs due to differences occurring in various implementations. For instance, different data formats used in music or different parameters used to load data. The third keyword is generalization. Generalization has gained attention due to the rise of machine learning. The thing is that we need to increase the number of well-annotated datasets for training effective models. Many of the MIR methods are trained on datasets, very little datasets, and they have a low ability to generalize when tested on different datasets. The design principle that moved our effort are 6. The first one is generalization. In this case, we mean the ability of including different datasets which are distributed with various formats. So we want a framework that is able to provide multiple datasets, even if they are distributed with different formats. Then we want modularity. So we want to be able to use datasets in different contexts. For instance, we want to reuse existing utilities to include additional datasets, or we want to use only some part of the datasets, not all of them, and just some annotations. And then we want that the framework is extensible. So the end user should be able to convert from existing formats to take advantage of the API that the framework provides. And we want that new datasets can be added without having to edit sources of the framework. Then we want that the end user is able to do set operations over all the datasets provided by the framework. For instance, one of the major trends in music performance analysis is analyzing piano music. This is because we have these claviers or similar piano, which allows us to record very precise MIDI recordings. But there are also other instruments other than piano, and a recent trend is to focus on other instruments. But we have few data, and the annotation of this data is very time expensive. So one thing that can help is to merge different datasets and take all music pieces using violins, for instance, or using flutes from different datasets. There is another point about copyrights, because we want that all datasets provided by the framework are downloadable from their official sources, so that we don't have problems with copyrights. And then we want that the framework is audio to score oriented. Of course, this is just for now. This is our major concern, because the framework is poor in an audio score research. So we augmented all the data available to increase the alignment data usable in our research. This is a picture which shows the overall infrastructure. As you see, the API is the main object from the end user perspective, and the API contains references to the official files, JSON files, but it can also contain references to custom files. In particular, there are two kinds of files. There is datasets.json, which contains the reference to a dataset directory. This is the official one. This is the custom one. We can use different datasets.json, for instance. And then there are the definition files. So maestro.json, backend.json, smd.json, and so on, which contains references to the single files inside the dataset directory. Everything is relative, and everything is very modular and can be distributed on different hard drives. Dataset definitions, so these other custom definition and Maestro, Backend, and SMD. A dataset definition is essentially a JSON file which contains generic description of a dataset. These are some example of fields contained in a dataset definition. For instance, we have the ensemble. Can be true or false if the dataset contains ensemble music pieces or not. Instruments, the list of instruments used, the recording format, the installation command needed to download the dataset, the ground truth type contained in the datasets, and the list of songs with other attributes. And once a dataset has been described with a dataset definition, which must be done by hand, we can use the dataset definition out of the box with our API and together with other dataset definitions or the official dataset definition. So everything is very modular. The annotation files can be stored anywhere else, and there are three different levels to describe the ground truth. So each dataset contains a list of ground truth, and the ground truth contains all these parameters, so precise alignment, broad alignment, and so on. Each one of these is a ground truth type, and each one of these is associated with a values, which can be 0, 1, or 2. 0 means not available for a dataset, and 1 means that it's available and has been manually notated, and 2 means that it's available and it's created by some state-of-art method. As I said before, we augmented all the data with alignment. We have only few datasets which contain both music score and aligned data. So we analyzed these few datasets and computed the histogram of the mean deviations of the nodes and the histogram of the standard deviations of the nodes. Actually, the mean is computed per piece, while the standard deviations is computed per nodes. So this is slightly different. We end with 4 different histograms, 2 for the onsets and 2 for the offsets. And so we have onset mean, offset STD, and onset STD. And note that these onset and offset actually are onset deviations and offset deviations from the aligned data. Then when we have a non-aligned piece, for instance a piece recorded by a disc clavier, we take an onset deviation mean from the histogram of the mean and for the whole piece, and an onset deviation STD for each node, and we add it to the onset mean and get an inferred onset deviation. This happens the same for the offset. Okay, this is just a simple way to reproduce a distribution of the deviations, but there are actually no effective method as of now to infer the music score from a music performance MIDI. And so for now we are still relying on this simple method. By the way, we empirically checked that the alignment methods, the alignment state-of-art alignment algorithms work almost the same on music scores and on inferred misaligned nodes. The API are written in Python, so they basically are written in C. They allow to load different definitions other than the official ones. They allow to filter the dataset based on attributes, to retrieve data with different kind, like piano roll or the note matrix, like the MATLAB toolbox or the MATLAB MIDI toolbox or raw data. They allow to parallelize the computation over all the songs, and it's completely compatible with PyTorch. Now let me show you a couple of use cases. The first one is when the user wants to use our framework to convert an existing dataset. In that case, he just has to describe how to convert from the input file format to the output to our annotation type. For now, he still has to do this command, the copy prototype GT. It will be not needed in future when we'll completely move to a object-oriented approach. But for now, this method is still needed, this command. And afterwards, it just open the file, in this case a CSV files, and fill the dictionary. This prototype GT is basically a dictionary, an empty dictionary with the correct fields. And the magic happens here in this convert, which allows the framework to apply this function over all the files. In this case, we show a couple of methods. For instance, here we instantiate a dataset class. We filter it according to the specification. In this case, we take all music pieces with piano, which are not ensembles, so solo piano, written by Mozart, and which contain a precise alignment annotation. We can get the raw data, we can get the mixed track, the ground truth path, we can get the piano roll. In this case, is the piano roll with timings referred to the non-aligned data, so to the inferred data. And here we show that we can just define a function which works on a given data set and on a given index on the data set, and we can process a song inside this function and then apply this function in parallel to a whole data set. In this case, the data set is filtered by violin. The third use case is when a user wants to use PyTorch. In this case, he just has to write his dataset class as would do in PyTorch, but he just has to inherit from dataset. In this way, he can filter the dataset, and in the getItem method, for instance, we can get the score or get the piano roll and convert it to tensor and send it to the GPU and so on, and we can iterate over this my dataset object to have all the magic of PyTorch, which is able to load data using the CPU while the GPU is working on other data and so on. This is our short to-do. We can, of course, improve the conversion procedure, as I said before. As suggested by reviewers, we can study the user experience. We can add, for instance, the estimation of the download time needed for each dataset, and this can be useful, for instance, if in a music computing class one wants to let the students try to test some experiment on a little dataset. We can add new annotation types. We can leave the user the ability to distribute only some of the annotations. Of course, we are open to any contribute, any perspective, any advice. There's also another project written in Python about datasets for music information retrieval, but this project in particular is about multimodal. So if you are interested in music information processing with multimodal approach, just have a look at the paper, let me know, and I'm sure that you have something with which you can contribute to this framework. You can just install the framework using pip. This will install the Python code, but then we need to load and install the datasets with this command. And here are the links for the docs and the source code. Thank you for your attention.
Hi, my name is Laura Bishop, and I'm a postdoc at Ritmo at the University of Oslo. My research looks primarily at social interaction and coordination in music ensembles, and a large part of this involves studying musicians' body motion when they are performing together. In this presentation, I will be talking about a comparison that we made between two infrared motion capture systems during a recording session with a string quartet. There are different types of motion capture technology that are regularly used to capture human motion. These range from video, where you can apply different computer vision and pixel differencing techniques, to inertial sensors, which sit on the moving body and typically track some combination of orientation and acceleration, to optical motion capture, which uses triangulation to track the position of certain markers in 3D space. This is the type of motion capture that we're talking about. Our comparison was between two passive tracking systems, which use infrared to track the position of reflective markers through space. Some previous studies have been done to compare mocap systems in terms of noise level or drift. Our experiment here looked at tracking reliability, including noise level and drift, for both stationary and moving markers. At our center, we apply motion tracking to a variety of different scenarios. Some involve capturing fairly large-scale motion, like musicians' bowing gestures. Others involve capturing quite fine-grained motion, like pianists' finger movements. There are also some studies that have looked at motion during standstill. We know that different types of motion provide different challenges to mocap systems. For example, with standstill, your data can be easily degraded with high noise levels. And for situations with higher amounts of motion, in particular with faster velocity, so you have to ensure that your tracking system can sample the motion data at a high enough frequency so that it doesn't lose track of the marker as it's moving through space. So we compared a high-end mocap system with a mid-range mocap system. And it's important to note that the high-end system that we used was about 10 years older than the mid-range system at the time of these recordings late last year. To tell you a bit about the framework of these recordings, we basically had the opportunity to do a recording session with the string quartet from a music academy nearby us. This session had two aims. First, we were making an empirical test of some hypotheses relating to inter-musician communication. And two, we were testing equipment in preparation for a later study. We ended up with successful recordings of the session from both mocap systems, which allowed us to make the analyses that I will present in a moment. So we made a total of 7 recordings. The musicians were seated in the center of the capture space, and they made multiple performances of one particular piece, plus some additional performances of other material. For most of the performances, they were configured as you see in the picture here, which is the normal configuration for a string quartet. But for some of the performances, they were configured differently, for example, sitting back to back. The musicians wore 6 body markers each on the head, back, and 2 on each arm, plus 4 markers that were attached to eye tracking glasses that they were wearing. And these comprise our moving markers. We also had 4 markers attached to each of the music stands, and these comprise our stationary markers. So here at the right, you see some examples of trajectories of stationary markers. The position values here are given in terms of the marker's distance from its starting position. This is done so that we can see the position values for the two systems together on the same axes. You'll notice that there's a small degree of noise in all of the signals, and there are also some what we could call instantaneous spikes. For example, in the top plot for the mid-range system in blue, there are a couple of these spikes. And then in the second plot, the middle plot, for the high-end system in red, there's a small jump that takes place around 35 seconds, where the position of the marker changes very, very slightly and continues in the new location for a period of time and then goes back to its original location. So we observed some different types of noise here. At left, I've listed the variables that we looked at for stationary markers, which I will explain in a moment. For moving markers then, at right here you see a few example trajectories of some of the cellists' markers. These are also represented in terms of their distance from their starting positions. As you can see, the trajectories recorded by the two systems are almost but not quite identical. And in particular, if you compare the first plot on the top to the second one, you can see that some of the markers recorded with higher degree of similarity between the two systems than others. For moving markers, we looked primarily at the magnitude of error or difference between the systems as a function of quantity of motion. So we looked at the noise level in stationary markers by measuring quantity of motion measured in millimeters per second. You can see our results in the plot to the right. We actually found higher quantity of motion, so higher noise, in the high-end system than in the mid-range system. And this was the case for all of the 7 recordings that we made. You'll also notice that quantity of motion generally increased across recordings 1 through 7 for both systems, which suggests that precision decreased over the course of the several hours that this experiment was running. We also looked at the spatial range that was captured by the two systems. This is measured in terms of the difference between the maximum and minimum position values. You can see the results here in the plots. Again, for all of the 7 recordings, we found that the high-end system had a larger spatial range than the mid-range system. So this again indicates a different form of noise level. Finally, for stationary markers, we looked at spikes. In the plot at the bottom, you can again see some examples of spikes in the signal. We looked at how often spikes came up, and we found that there was a consistently higher rate of spikes in the mid-range system than in the high-end system. So this was the case for 6 out of the 7 recordings that we did. For moving markers, we tested the hypothesis that the error between the systems, the magnitude of the error between the systems, would increase as quantity of motion also increased. And as you can see from the graph at the right, we did find, in fact, a pretty strong correlation between quantity of motion and between system error magnitudes. You can also see this in terms of the average between system error that we got for markers that sat at different locations. For example, for back markers, the back didn't move all that much and the error is quite small, but for the glasses, which moved quite a bit more, the error was bigger. For moving markers, we also made an analysis of the magnitude of errors for each of the x, y, and z dimensions. We found that the smallest errors occurred in the y direction, which was the vertical direction in this experiment. And it's interesting to note that quantity of motion was also lower in the y direction than in either of the x or z directions. So this may have played a role. So to conclude, I just want to summarize our results in terms of how they might be informative to people who are designing mocap experiments. First of all, we found that the older high-end system recorded with higher noise than the newer mid-range system. This is the case both for quantity of motion and for spatial range. So even though high-end systems like Qualisys can be preferred for some of their features like higher frame rates, better labeling algorithms, more affordable systems do give very high quality data at this point. We also made the important observation that between system errors increased with increasing quantity of motion. This should be noted in studies where large amounts of motion are expected and probably accounted for with smoothing. And this should also in particular be noted in studies where precision is important. For instance, if you're looking at fine-grained motion like rapid finger movements. We did not find substantial drift within recordings, but we did find that recordings became less precise over the several hours that we were running this experiment, which shows how important it is to recalibrate if you're going to have a very long recording session. And I also want to note that we observed poor tracking in markers that were located near the edge of the calibrated space. This manifested in terms of high dropout as well as very high noise levels. We actually excluded these markers from our analysis because they were quite clear outliers. So this shows how important it is to make sure that your markers are centered well within the space that has been calibrated. Finally, I just want to thank our collaborators at Ritmo and of course the musicians who participated in this experiment, and thank you for your attention.
All right, so thanks for these great presentations and projects. This is the Q&A, and so the idea here will be to gather questions from the audience, from the chat, and maybe we can do a round of one question for each, and then ask more questions in terms of group questions. So we will start by sequential order, and we have a question from Andrea, actually, that goes to Hans. And the question is, do you think that your XML format can have a more general usage for encoding audio process and HCI interaction? For example, not limited to your specific application?
Yeah, that's a very interesting question, because we started off with this as being something for the web, using WebAudio API, but we had some discussions when we realized that this is actually kind of opening up for language to describe the connection between an interaction and an audio configuration. So yes, I think there is a great potential actually for like working on a language for describing those general things.
Great, thank you. And we move to Shin. So Shin, you mentioned in the paper, you mentioned that the current version, so it's built upon a previous version that was on Unity. So I was wondering, what are the advantages of using the web platform, and what do you miss from the Unity environment?
Yes, web. Web environment is very easy. So Unity is needed a dedicated application, but web application is needed only web browser. So it is merit of our systems.
Thank you.
Thank you.
Yeah, and yeah, we just moved to Federico. So Federico, in your paper, you mentioned that you're planning to study the user experience of the framework. So can you outline what do you envision how this evaluation can look like?
Well, probably what we are doing is to let's try the framework, which is written in Python. It's targeted to developers, so probably we will ask to some research scientists to use the framework and to download it, install and test it, and we will just ask what they think and what could be the improvements with a very easy open questions and open answers. Not a real very precise plan for now, but we are open to any kind of suggestion.
Okay, thank you. And we move to Laura. So I just wonder how similar and different would be the results if you analyzed a different musical activity. And you mentioned the standstill. So I guess the extreme case would be a standstill. I'm not sure whether that would inform much, but yeah, how different would the results be?
I don't think the results would necessarily be that much different. The types of movement that we captured here were head movement and arm movement, which captures a pretty good range of what people tend to do. Perhaps if we were to compare something very fine-grained, like pianist hand movements, this would be perhaps interesting because it's quite a lot of movement, but it happens in a very small space. So this probably would be an interesting comparison to make. And in terms of the standstill, well, some of these analyses have been done previously in preparation for looking at markers that are standing very still. So some things that our colleagues are working on are trying to separate the noise out of movement that actually happens when people are standing still, and the markers are almost stationary but not quite.
Mm-hmm. Thank you, Nora. And so, well, looking at if there are any questions, feel free to post those in the chat. And if not, I have maybe like a group question for all of you, given that this is a session on hardware and software, and all of you in your papers discuss about the standards in a way or in another, how to have a dialogue with standards and also make a sustainable progress of the code. So any thoughts for your respective projects on what are your plans in terms of making the code, or I mean, making the code according to certain standards, and if there are not standards, what would be your contributions? What are your thoughts?
Well, there are a number of standards for music representation in various formats, and we at LIM in particular in Milan, we develop a standard for multimodal representations, which actually is under reviewing in this moment. It's called the IEEE 1599. So that can probably be a suggestion, but well, it's based on XML, and maybe of course some revisions are needed. And also there are other standards for music representations in various formats, like the AMI or the Music NX that is developed by the W3C committee. And so it's a topic of research in trend right now, and probably the SMC community can give its help in developing new formats.
Yeah, I'm looking forward to see if we can do something with WebAudio API, XML, and then connect it to platforms like PD or other standards that we're using in this community. That I think every attempt to do something standardized and to meet with different technologies will open up endlessly of creative ideas and projects. That's very exciting, I think.
I guess for me, there's in the world of motion capture, there's a number of different systems that are quite standard across and quite commonly used across different institutes. So checking the reliability of each of these against each other, and noting, of course, as we saw in our study, that these results change quite quickly as the systems get slightly older. This would probably be valuable, and also to check this against different types of motion capture that can be used in different situations. So versus just what you can take from a video camera in a more ecological situation would be useful.
Shin, would you like add anything on Web 360?
Yes. Sorry.
Well, you talk about this consortium, for example, in your paper, the software-defined media consortium. So what is the role when deciding?
Our systems, and in our systems, there are many bugs now. So we have to approve and add features and fix bugs on our systems in the future.
Okay, thank you. And so let's check again if there are any questions in the chat. And okay, there is one question. I think I'm not accustomed by Rares A. I am not accustomed to WebAudio API, but what would the authors of the paper consider to be the biggest limitation of their proposed standard is in terms of sound synthesis capability?
So I guess that question is for me. Well, what we present is not just so we understand each other. It's not the technology that makes the sound at all. It's just a way of describing how that web audio should be configured in an application. And there is a lot of discussion going on if like web audio API is a useful tool, what you can do with it, if the performance is good enough, all sorts of questions. There has been a huge step forward with a node called Audio Worklet, and using that node you can build kind of like whatever you want to do. And I think that's the way WebPD is implemented into web pages, for example. Then performance-wise, I would guess it's still problems related to using a web browser to do fancy audio stuff. But I'm just very I just think it's so interesting with the web technology, even if the performance is struggling a little bit at the moment. It's so interesting to see where we're going in the future, and I just think it will be a very important platform. And our attempt to specify that using XML is just like a first attempt, like a first sentence in the question. So let's have a dialogue about what we need to express and what we need to sort of define when we build things like this.
I also had a question for you, Hans, about why did you choose XML and not JSON? That's kind of explained in the paper, but lightly. So I just wonder, can you?
That's a very pragmatic decision. So I found that my students generally understand HTML quite well. And as soon as we get into, brackets, dots, curly brackets and stuff, they just get disorientated and they miss a little sign and it's just very corrupt. So they found it somehow easier to do it with XML. So that's the only reason. I know there are definitely downsides using XML as well. It gets quite big in terms of code and stuff. But the response from the students was very good. They see and understand what they're trying to do. So that was very positive feedback. And we are right now working on a follow-up study on 25 projects using it. So it's exciting to see.
Perfect. And so, Rares, thanks for the answer, by the way. Are there any other questions from the community, SMC? It's now your opportunity to ask questions. Yes, well, the chat is a little bit quiet, but then just to ask you all if you have anything else that you would like to add or complement from your presentations. No? Well, so then we can perhaps conclude this panel. I really, thank you for your nice presentations and contributions.
Thank you. Thank you very much.
Thank you so much. And yes, and just, please, there are applauses we can hear, so please keep, the next session of the SMC, which are the posters. Thank you.